In any case, the organizers asked me if I'd be willing to chair a session. I'm very happy to do that. But I was particularly happy to chair this one because it's really the future directions and the depth and breadth of discovery that we're experiencing now that are going to drive the next 10 or 15 years. You can already begin to see the influence of some of these. And the talk that got delayed a little bit due to the presentation will be on second primary cancers. And that's being driven largely by the ability to use carbon and light ions for therapy on very young people. And you've still got the neutron production problem. So in any case, our first talk this morning will be individual radiosensitivity and possibilities of prediction. Simon Bouffler, Public Health UK.
First, I must say a very big thank you to the organisers. I feel it's a great privilege to be with you presenting today on this rather important occasion of this 90th anniversary year for both ICRP and ICRU. And I hope that I'm able to provide some insight into what might be a factor to take into consideration in the future, and that is variation within the population in their response to ionising radiation and how that might have some practical implications. But I must also say a very big thank you to the organisers for their absolutely outstanding hospitality during these past few days, and most notably for the dinner last night, which was really a very special occasion for those of you who were there will certainly know that. So, title, Individual Radiosensitivity and Possibilities for Prediction. So what is this about? So, current system of radiation protection, as you all will know, aims to avoid tissue injury, or otherwise known as deterministic effects, in perhaps a former term used, tissue injury is preferred these days, and minimise the risk of stochastic effects, and those are cancers and hereditary effects arising after exposures to ionising radiation, generally at the lower doses, but also occurring at higher doses, of course. And that system of protection works by justifying practices, optimizing uses of radiation, and dose limitation when required. And those dose limits are derived not from real people, but from a notional average person that doesn't really exist. They're averaged in terms of age and in terms of gender. So that is not reality, in a sense, but it does work for practical purposes. So obviously, we are all different, and to use a local analogy, Benny was the one with a beard, Agnetha had blonde hair, and Ifrid had dark hair. But more seriously, there are known gender-specific differences in risk, especially in the breast, as a prime example, perhaps, where epidemiological studies show us that the excess relative risk, ERR, for incidence of breast cancer is 0.58 in females versus a much lower 0.35 in males. And there's an age dependency of risk, with generally children being more sensitive than older adults. So there are, we must note, a number of different ways of, if you like, measuring or assessing radiation sensitivity or variations in response to ionising radiation from different levels of biological organisation, from the whole organism level, up at the top there, using assays like the old-fashioned, if you like, LD50 type assay. You can see variation there. In clinical reactions, we heard about the radiotherapy and the fine-tuning that's actually possible now in radiotherapy. Unfortunately, there are occasional overreactions, adverse reactions spotted in clinical situations, and that's observable, quantifiable, and I'll show you one example of that at least. There's also indications that susceptibility to radiation cancer varies between individuals that are exposed in whatever situation, really. There's evidence from epidemiological studies, for example, there. Tissues vary in their radiosensitivity, and that's reflected in the ICRP system of protection in the tissue weighting factors, which vary between different tissues. And finally, a large class of tests, if you like, or assays that are available at the cellular level. So ideally reflecting what happens higher up the biological organisation chain, if you like. Things like cell killing have been used, and chromosomal damage, DNA damage, and an ever-increasing battery of tests there, or approaches to experimentally assess sensitivity to ionizing radiation. And I think before going further, I need to sort of maybe take a little pause to talk a little bit about definitions of radiation sensitivity or radiation response, because there has been actually quite a number of publications in the recent year or two on this topic, in that Britell and colleagues in 2018 suggested a particular use for terms in this area. And their proposal, as you can see here, was to restrict the use of the term radiosensitivity to any clinical or cellular consequences of radiation attributable to cell death. And that's in contrast to the term they propose, radiosusceptibility, to describe radiation-induced cancers or any feature that's attributable to cell transformation. So making a distinction between cell-killing driven effects and other effects based on cell transformation. I and others, and notably Andrei Wojciech, who's in the audience today, I know, are not convinced by this argument, in that, for a number of different reasons. The terms, at least in English, susceptibility and sensitivity, are really considered synonymous. If you look in the thesauruses, you'll find that they are listed as synonyms of each other. The common antonym for both susceptibility and sensitivity is resistance. So there is still scope for confusion by using those terms in very specific ways, as suggested by Britell et al. And also, perhaps most importantly, the very precise use of these terms for different types of sensitivity maybe suggests a greater understanding of the mechanistic basis behind the phenomena being described. So I think we're just sounding a note of caution, and I think there needs to be further discussion to come to a common terminology to apply in this area. So moving on to look at some actual information about the range of radiosensitivity that one can detect in populations. This is one example of a study conducted by UK colleagues led by Gillian Barnett, published in 2011. And it was used in a report that I was involved in facilitating by my employer at that time, Health Protection Agency, and its advisory group on ionizing radiation. And much of the material I talk about today will be actually derived from the experience of that and a few examples from that report. So these are 1,000 or so breast cancer patients treated by radiotherapy, taking out all residual confounders, if you like, of variation in sensitivity, to do with the dose, body size, and so on and so forth. So all the patient-related and treatment-related factors are accounted for, leaving a residual score, which is a reflection of the level of radiation sensitivity, clinical radiation sensitivity, with a higher number being a stronger reaction and the lower number being a lesser reaction in the normal tissues, not in the tumor tissues, a normal tissue reaction. So obviously a largely bell-shaped curve, if you like, with a mean with residual of 0, but notably a tail, if you like, an extended tail on the side of the radiosensitive group. So there are clinically observable variations, and one is particularly perhaps concerned in a clinical setting for those whose normal tissues are over-responding to a therapeutic regime, because those are the ones developing the severe reactions that one wants to avoid in a clinical setting. And if you look at the range of factors that do impinge on that distribution, it's known that increasing age can affect radiation sensitivity to normal tissue sensitivity after radiotherapy in adults. Smoking history does also have an impact. There's pre-existing conditions, notably diabetes and collagen vascular diseases, can impact on the, or have been shown to be associated with higher sensitivity of normal tissue to damage in radiotherapy studies. And there's also a contribution of genetic factors is understood to be in play. There's lesser evidence for things like sex, ethnicity, body mass index, body size, basically, diet and alcohol. But there is quite good evidence from these clinical studies. There is a range. So it's not like a notional issue, variation, but it's a real issue. In addition to observed phenomena in clinical studies, various, there are some well-characterized and well-known radiosensitivity syndromes out there amongst the population. These are generally rare recessive, genetically recessive disorders that lead to increased cellular and sometimes clinical radiosensitivity. All of them, unfortunately, have long names: ataxia telangiectasia, Fanconi's anemia, Nijmegen breakage syndrome, Cornelia-de-Lange syndrome, and severe combined immunodeficiency. That's not a full list, but that's some of the more, the best-known ones, perhaps. And these all have a genetic basis, but these are rare within the population, usually on the order of 1 in 10,000 live births or something of that order. So they're not common, so they're not a large population group to be concerned about in terms of radiological protection. You can also observe some other genetic factors coming into play in pediatric subpopulations, those carrying certain genetic deficiencies in, for example, retinoblastoma gene or the neurofibromatosis gene, Li-Fraumeni syndrome, and nevoid basal cell carcinoma syndrome, sometimes known as Gorlin syndrome, do show, after radiotherapy for a primary cancer, increased risk of secondary cancers. And that's perhaps most notable in the Li-Fraumeni syndrome. These are patients with deficiencies in the P53 gene with a higher relative risk of secondary and even tertiary cancers after therapy. So there's two examples there of genetics clearly having an influence on radiation sensitivity within the population. And because of that, you'd predict that you can detect some sort of more mild impacts of genetics when you're not having symptomatic patients carrying these disorders, with the disorders, but those who are carrying just one abnormal copy of the given gene. ATM is a gene responsible for ataxia telangiectasia, the gene I mentioned first on the previous list. So heterozygous carriers of a defective ATM gene have an approximately twofold elevated breast cancer risk per se. That's not with radiation. There is some indication that some ATM variants carry a somewhat greater risk of contralateral second breast cancer. So these are patients who've had radiotherapy for a primary breast cancer, but as a consequence of that, they develop breast cancers in the contralateral breast. Obviously, an outcome of radiotherapy one would want to avoid. And there's a few, perhaps not so strong, so-called case-only studies, so you're not doing case-control type study design, where there's indications perhaps that the BRCA1, BRCA2, and CHEK2, the well-known breast cancer susceptibility loci, do increase the risk of secondary breast cancer. Perhaps not the best studies in the world. So while there is some evidence there, that, how difficult is it actually going to be to identify all the factors, genetic factors, contributing to radiation sensitivity within the population? Well, just for one example, the WeCare study, a large study of more than 50,000 women in the US with breast cancer, and there was a study nested within that of 700-odd contralateral breast cancer cases and suitable controls, looking at a number of different gene variants and other factors as well, actually, looking to see whether there was or not increased relative risk of contralateral breast cancer due to these factors. And generally, the results were quite negative in that for the CHEK2 variant, there was an increased relative risk, but it wasn't significant. For a full scan of the ATM gene, which is a large and complex gene, one rather rare variant within the population did have an increased relative risk of contralateral breast cancer. SNP analysis within the same gene, no associations. BRCA1, BRCA2, no associations. And some SNPs in a variety of breast cancer loci, no associations. But pregnancy factors, there was one strong association. So it's actually basically quite difficult to find these genetic variants out there in the population, even when you're dealing with subjects who are effectively quite heavily irradiated. This, again, radiotherapy setting, so you're not talking about low doses where radiation protection generally operates, but in the more clinical medical setting. Important nonetheless, but remember it's high dose when dealing with here. Is there any evidence from lower dose situations? Diagnostic exposure would be an example of that, again, in medicine. Some, perhaps again, rather a weak sort of clinical trial or medical follow-up type studies of BRCA1, BRCA2 carriers, suggesting some increased relative risk of breast cancer following multiple chest x-rays. That had a major problem that the radiation exposure assessment was by individual recall of the exposures that they had, so not the strongest study design you would want to really be confident in any results coming from such studies. Looking again at the BRCA1 and BRCA2 genes in a mammography setting, obviously widespread population screening for mammography. A review by Amy Barrington Gonzalez in 2009 really determined there was mixed evidence out there from the studies available, but ultimately concluded that there was no substantial risk as long as you restrict screening, routine screening, to beyond 35 years and beyond. So that's a quick run through some of the genetic factors that might be underlying variation in radiation sensitivity. Are there other things? Well, the answer to that is clearly yes. This is a table taken from that advisory group on analyzing radiation report I mentioned, looking at the additional cumulative absolute risk of radon-induced lung cancer. So this is not a medical study. This is a residential radon study, basically, per 100,000 people. So this is the radon exposure level given on the left-hand side here, from 100 to 800 becquerels per cubic meter squared within the home, comparing the risk in smokers and, non-smokers and continuing smokers in column B. And you can see the numbers are really quite substantially different. And the ratio between the two is on the order of 30. So here we have clear evidence that if you might say, environmental or lifestyle factor is impinging on the risk of radon-induced lung cancer. A well-known example, indeed. But you know, still, the size of that difference is so much larger than the sizes of differences that are being seen in those genetic association studies I was talking about just a moment ago. So, what about other things? Diet. There's been a lot talked about diet and obesity and stuff in the past few years within public health generally. And I work for a public health organisation, so I can't help but to get exposed to those sort of discussions and those arguments. And it is actually well understood, and you even see this commonly, certainly in the UK, in newspapers, that dietary factors and certainly calorie restriction can extend lifespan and reduce cancer burdens. That is known. That's not just a theory. There's good evidence behind that. But in addition to that, maybe less well known, is that dietary restriction or calorie restriction is known from some experimental animal studies to modulate cancer incidence. And there's evidence for that since a long time, since the 1940s. So again, another lifestyle factor impinging on risk, effectively. And that's assumed to be driven by so-called epigenetic modification of gene expression. Epigenetic modifications are a wide group of changes, not to DNA sequence, but to modifications of that sequence by methylation, acetylation, and indeed not just the DNA sequence itself or the DNA itself, but by the surrounding chromosomal proteins, histones, notably acetylation modifications there. So a large and complex class of epigenetic changes, and that has been reviewed by one of my PhD student colleagues relatively recently, and I'd encourage you to have a look at that to be a bit more convinced than I can actually have the time to talk through today. So that really leads to the question, if we know there's some genetic factors, albeit maybe not that strong, and some other factors, smoking and diet being the prime ones I've shown you here, is there any way of kind of integrating the information between those two things with a view to being able to assess individual cancer risk? Well, some of you might have also come aware, because it has been covered a bit in the wider popular press, about things called epigenetic clocks. These are based on the methylation status, so one of these epigenetic modifications, of a subset of sites that alter predictably with age. So you can actually determine the biological age of somebody with really quite some accuracy, remarkable accuracy. And clocks can be slowed, the sort of ticking of that clock can be slowed in those who adopt a healthy lifestyle. So the biological age of somebody adopting a healthy lifestyle doesn't run as fast, if you like, as one adopting a less healthy lifestyle. Clocks actually predict time to death, which is actually slightly concerning for me. I've not had a test done yet, but I'm not sure if I intend to. Obviously, that precludes being run over by buses when you're coming back from lunch, but you know, there's really quite sound evidence for that. These are based on actually quite detailed, in-depth, sort of artificial intelligence-driven analysis of large data sets to be able to actually tease out this information. So it's technically quite complex. In addition, those clocks run fast in those with progeria syndrome. So again, evidence that these clocks are really measuring something of biological reality. And they also run fast in those with non-communicable diseases, such as cancers. It's also known that environmental agents can actually speed up the ticking of those clocks, if you like. And the best example, I think, at the moment that I'm aware of, at least, comes from air pollution. Air pollution is obviously another major public health concern within all nations of the world, I think, be it industrialized nations where traffic is the largest problem, perhaps, and less developed nations where indoor cooking and fumes from that are a significant problem as well. They also speed up the ticking of the clock as well. So it leaves the obvious question, what will radiation do? Well, there is some limited evidence out there, and I won't go through it because it's very, very incomplete at the moment, but a more detailed look at these epigenetic clocks I think is very much worthwhile doing. And there's one review article. Steve Horvath is one of the main players in this field, and he's done a lot of really very impressive work, drawing on community-available resource from the methylation data sets and applying his expertise in artificial intelligence and machine learning to these things. So that's one potential route into prediction. But so what's actually been done about prediction? When you're thinking about designing ways to predict radiation sensitivity, what would you have to consider? Well, which tests and which would be they genetic or cellular? Which populations are you going to apply that to? Medically irradiated populations or maybe in occupational settings? Which samples are you going to use? Blood, saliva, cell biopsies? You've got a range of options there. And not to forget that if you do testing, you've got to think about how you're going to deliver the results of those tests to the individual being tested. So there's clearly ethical considerations there. There are some substantial projects ongoing hunting for genetic predictors of radiotherapy, normal adverse reaction in normal tissues after radiotherapy. I've just noted one here, the Requite study, which is a European-funded study led by Cathy West in Manchester. They're validating predictive models and biomarkers in fairly substantial cohorts. They've collected close to 4,500 samples from cancer patients undergoing radiotherapy. Results are awaited, unfortunately, so I can't give you the answer. But in addition to, if you like, nitty-gritty genetic testing, looking actually at the DNA sequence to see if you can identify markers of sensitivity, cellular assays have been developed. Two I've noted here. The relative frequency of induction of apoptosis, that's a form of cell killing in T lymphocytes in those exposed in vitro, so a blood sample is taken from a potential cancer radiotherapy patient, should I say, and looked for association between the relative levels of apoptosis after the in vitro exposure to a pretty heavy dose, it must be said, 8 gray, and looking at correlations with late developing normal tissue reactions in a fairly substantial 400 or so person group, and there was an association found. More recently, ATM foci, these are nuclear foci reflecting the processing of radiation-induced damage. Foci accumulate in the cell nuclei, and taking skin biopsies from patients, looking at rather short times after exposure, published just this year. And this test is actually being proposed by a diagnostic company, the website of which you can examine at your leisure later. So that would be for predicting therapy outcomes. So some possibilities, I think, is the strongest I would put it. What about diagnostic? Obviously, again, dealing with much lower levels of exposure, it's going to be much more challenging to find any real strong associations. So gamma H2X foci, again, another nuclear focus, part of the damage response kind of mechanism after radiation exposure. Into low dose this time, 2 to 4 milligray exposed mammary epithelial cells taken from individual patients. There was more foci seen in cells from patients with high breast cancer risk or familial than in those with low breast cancer risk. So some cause for optimism perhaps in that. But there's absolutely no doubt it will be more challenging to identify variations in response to lower doses. So that leads you to think about how you might actually, given that there is possibility, and I wouldn't put it more stronger than possibility, of prediction through genetics or epigenetics, what would you do with that? So how would you utilize that knowledge? You clearly need to have reliable prediction, and that may be in the form of genetic testing or cellular testing that I've just sort of outlined a few examples of, or these epigenetic clocks I talked about a little bit a few slides ago. Certainly that will require accuracy, speed, reproducibility and transferability between labs or centres. That would be critical to make sure we have a really robust test. And acceptance that it's the right thing to do. And I don't think that's there yet. There's a lot to be considered. Which leads you on to thinking about ethical considerations. In a sense, links a little bit to the very nice talk from Nicole earlier on today. That if we did have the ability to identify sensitive subgroups or individuals within the population, you'll need to have a very careful think about what you do with that information should you determine you should do something with that information. And that would become particularly pointed, I think, in occupational settings where I'm involved in some discussions with the UK nuclear workforce on the epidemiological studies that PHE run, and you do have to tread very carefully in occupational settings for introducing changes of any sort. And this would be a very substantial change. And you'd have to consider the principle of ethical justice, if you like. If it is only small numbers of people you're aiming to protect and they're at rather higher risk, and would the resource spent on protecting small numbers be justified ethically? But in the absence of anything in the way of testing, which I think is broadly the situation at the moment, you can, it would be wise to provide information on other risk modifiers, things like smoking and diet, possibly, that should be the main focus. And indeed, in the UK, at least when we do radon remediation campaigns in the southwest and other areas, we do always bring along the smoking cessation people as well to make sure you have some integration, if you like, between the radiation protection aspect and the more general public health aspect. And I think that's a good way to go, generally, to try to integrate radiological protection as part of everyday public health as well. I think there's some advantage in doing that. So what would the requirements be, really, in the ideal world if one was going to adopt such an approach? Well, you certainly need a knowledge of the range of radiosensitivity within the population. That's perhaps the critical factor. How wide a range is it? How many people are on the very resistant end and the very sensitive end? We would really want to know that before moving forward. You'd certainly want reliable methods to predict that sensitivity, should it be there. You'd also want to have an agreement. There's benefits in utilising that information, should you be able to obtain it. You'd want to, and that's really the same thing, a robust framework in which to operate. So you'd want to know how you're going to apply that knowledge in a real-life situation, should you have it. And the acceptance by the wider workforce. And just on that point, and it's actually timely in a sense, and I didn't know this at the time I was invited to give this talk, but just in this past few days, ICRP has agreed to set up a task group on individual response to radiation. It's just been approved in the past few days. And I have the pleasure of chairing that along with other colleagues. So I'm looking forward to a few years of lively debate and discussion amongst ICRP colleagues on this particular topic. This has been said before today, but I'll put it up anyway. Don't forget, ICRP requires your support to do all the good work, like looking in a bit more depth at individual sensitivity, but notably the Free the Annals campaign ongoing, which Claire mentioned earlier on. And of course, you'd be very welcome to attend the ICRP 2019 symposium, which is a long way away. It's in Australia, but maybe you'd like a little joint work and holiday, I don't know. So really with that, I think I'll say thank you very much for your attention. Just to note, this is the front cover of the advisory group publication I mentioned earlier on. And for anybody who didn't get the kind of local cultural reference earlier on, it was these people I was talking about. So this one's Benny, this one's Agnetha, this one's Annie Fried, and that must be Bjorn. Thank you very much.
Thank you for such an entertaining and compelling set of remarks. We have a little time for a question or two, if there are any at this point. Yes.
No. Hello. Yes, it's on. Just to remind you, or a note, that Simon is actually not staying for the panel discussion. Yeah. He has an early flight, so any questions regarding radio sensitivity could be good to post now, just for information.
Now, and I'll be around over coffee break as well, and then I'll head off after that.
Thank you very much. Ted Lauser from the OECD Nuclear and Energy Agency. Simon, have you been looking into multiple stressors and the idea of radiation being one of the aspects of a long chain of things? And in that context, do you think that the AOP approach that's being done by the chemical people would be of use in terms of biomarkers?
Yeah, yeah. Personally, I'm not doing a lot on multiple stressors, but there are people doing that, looking at combinations of agents, basically, be they radiation and chemical or just chemical alone, and trying to work out how one best can assess the risk associated with those complex exposures, which undoubtedly happen in real life. I think the adverse outcome pathway approach has some promise. This is a way where you try and rationalize a disease pathway into a number of discrete mechanistic steps that you can quantify. And I would note that the US NCRP have got a scientific committee looking into this in respect of ionizing radiation. I know there's been some interest in Canada recently as well, a publication, I believe.
Another question over here.
Thank you very much for this review, Simon, of especially later data. And I completely agree that we have to look into the genetics. Besides lifestyle, certainly this is most important.
Yeah.
And we have to make the choice. Either we look for genetic mutations which are going to one specific cancer site,
Yeah.
one entity. For instance, for thyroid carcinoma, we have quite a number of genes where we know which are implicated.
Sure.
The other point would be to look for general phenomena in order to see whether there is an especially susceptibility for cancer induction. And we discussed this already.
We did, yeah.
On my point, genomic instability,
Yeah.
genetic instability is a very important point.
Yeah.
In all the syndromes which you showed, and you said that there are quite a number, further number of these syndromes, we see that genetic instability is increased.
Yeah. Yeah.
And usually this is connected to a decreased efficiency of DNA repair.
Correct. Yeah.
Quite often.
Yeah.
So I think one should look into this. And there are some possibilities for genomic instability to measure quite comparatively easily.
Yeah, yeah. No, I mean, just for others in the audience, I did have a conversation, I think it was just last night, with Christian Scheffert on this, and I understood that he and colleagues have been using a sort of genetic instability assay in a clinical setting to help inform potential overreaction of normal tissues, and that with some success. So that would be another one to add to the list up there. And certainly the syndromes I listed, the ataxia, telangiectasia, etc., do have DNA damage processing problems, if you like. So they do show genetic instability after exposure, sometimes before exposure. The however to that, though, is that in the genetic association studies that are available, and there are some, if you take a gene-by-gene approach and take, for example, the ATM gene, and look to see if that is associated with increased cancer risk after radiation, there are some data there, which I showed some of, but they're not that strong. So it seems that there will be factors in addition to those, what you might call genome maintenance factors, which are underpinning variation in response. So I think genomic instability will be part of it, but I don't think it's all of it.
Well, I only agree in part.
Okay.
For we have done studies looking into cancer patients and looking for lymphocytes, which are normal cells, not cancer cells.
Yeah.
And then into controls, persons who had not developed cancer, and we see a clear difference.
Okay, okay.
And
Well,
this is highly significant.
yeah, okay, thank you.
We do have time for one more, perhaps in the back.
Roger Coates from the UK. The factor 30 sensitivity between smoking and radon is extremely interesting, isn't it?
Mm-hmm.
If the radon standard is set on an average, what does that say about the value for money in remediating a domestic dwelling where there is no smoker living?
Well, I'm not sure if I'm the only person that in the room that could answer that question, and I'm certainly not the best qualified, and it's really essentially a value judgment that one's making there. It does impinge on the point that I made around testing, genetic testing or cellular testing, where you have to consider the justice in the resource expended on any particular measure, whatever it might be, to identify people or to remediate their homes. You know, I don't feel that I am, as an individual, able to answer that actual specific question, because I think it's more of a question one would have to discuss more widely. Personally, just a personal opinion, I would say anything one can do at relatively low cost, and radon remediation is not mega bucks, it's a few hundreds of pounds, I think. It's probably money well spent. And also, I'd note, in the UK at least, I think building regulations have been changed such that new homes have to have radon preventative measures installed as a matter of course, and I think that would be perhaps both cheaper and better way to progress in the future.
Thank you.
Good. Thank you very much.
So maybe, as you know, we're going to defer LeBaron Jacobs to the coffee break. So Wolfgang Müller from University of Duisburg-Essen is going to talk about attributing health effects and inferring risks at low doses, challenges for the next decade.
Okay. Yeah, first of all, thank you for the invitation. I feel very much honored by this invitation, and I hope that I can tell you something about attributing health effects and inferring this at low doses. You will see I will extend the term low doses a little bit into the medium dose range, because otherwise I could have a very short presentation just saying, no, you can't. And then I will sit down and will take your congratulations for such a concise talk. No, of course not. But you will see where the problem sits. And first of all, we'll tell you something about the attribution and then the challenges for the future. And first of all, two basic remarks, because there's a lot of confusion in that field. Because you have to be very careful to distinguish health effects, so something that is actually observed, and health risk, something that is expected, but you never can be sure whether your expectations will come true. Quite frequently, these are mixed, these two things, and this always is a problem. Because in general, health effects are related to the past, so you have observed these effects, and health risks to the future, so you have to make predictions for the future. They are always difficult. And something else you have to keep in mind, that it makes a difference to attribute in the individual case or in the case of a population. This will become clear in a couple of minutes. It's always a little difficult to define what is a low dose. A radiation therapist will think quite differently from a radiologist what a low dose. And so Ansky decided at least to give some guidance with respect to high and low doses. And you will see that high doses are thought about 1 gray, and in addition, moderate dose between 100 milligray and 1 gray, a low dose between 10 milligray, 100 milligray, and less than 10 milligray are thought of being very low doses. So actually my talk should be in that range here, but as I told you, I will extend it a little bit into the moderate dose, not to the high dose range, because then there is something else to consider, because when I restrict my talk to doses below about 100 milligray or a little more, then due to the threshold dose of about 1 gray for deterministic effects will not be addressed. So I will not talk about deterministic effects in this session. There will be one sentence with respect to that, but I will not go into the details there. So the focus will be on malignant tumors and leukemia. A few remarks will be on hereditary effects, cataracts, and cardiovascular diseases, but only very, very few aspects. So the problem, I think, is known to all of you. We have data up starting at about 100 millisievert that show a statistical significant increase in the number of cancer. With some fluctuation, but at least there are data with significant response. But what about the low dose range? In radiation protection, we use LNT. I will come to that aspect. But there are other possibilities. With respect to leukemia, it could be linear quadratic, or maybe even for solid tumors. There might be a threshold in the low dose range, 5 to 10 millisievert, for example. There might be some protection, hormesis, might be, or there might be a higher risk in the low dose range than expected from LNT. There are arguments for all these models, and it's very difficult to decide which is correct. I will come in the final part of my talk back to this question. So conclusions regarding LNT. A lot of biological mechanisms are affecting the response of organisms in the low dose range. I will show you some in further picture. Most, if not all, of these mechanisms show a non-linear dose response. In biology, linear responses are very, very rare. Mostly they are non-linear, maybe upward, maybe concave, or something else. In addition, individual differences are to be expected. Simon just talked about this problem. Thus, an exactly linear non-threshold response is highly unlikely. But for practical reasons, the convention to use the LNT approach in radiation protection is clearly justified. But don't expect that it will, the final result, when we ever come to this conclusion, will be LNT. One of the problems, we do not have a biomarker telling us this specific cancer case was induced by radiation. So we have about 20% spontaneous cancer death. After 1 gray, we have around 10% additional cancer death due to this 1 gray. But who are those 10% who will develop a cancer after radiation exposure? It could be these 10% or those or those. So you cannot decide because there's no possibility to identify a radiation-induced cancer right now. There's also, for most chemicals, no possibility. For some, there is. A few ones, for example, practically all skin cancers are induced by UV. And there are markers for that in addition. But in the field of ionizing radiation, up to now, we would be very happy if we had it. Up to now, there's no possibility to identify such cancer cases. So, but is attribution possible in population studies? And now you will see why I extend a little bit into the medium range, because if I restrict to 100 millisievert, at least for mixed populations, there might be a difference for the fetus, but in mixed populations below about 100 millisievert, you don't get statistically significant results. And yes, it is possible to attribute stochastic health effects in populations to ionizing radiation, but there are some caveats. But a serious problem in population studies is to overcome the statistical fluctuations. With decreasing dose, uncertainty increases, and unfortunately not linearly, but to the square. So the further you go down, the uncertainties will not go linearly down also, but you have to use the square. Thus, it's not surprising that for a mixed population, a statistically significant increase in radiation-induced cancer death is seen only from about 100 millisievert upwards, because the fluctuation, the normal rate is so impressive, unfortunately, so that you cannot find a slight increase in the low dose range. So is attribution possible in individuals are affected? No, it is not possible to attribute such stochastic health effects in the individual case to ionizing radiation. And the major reason, up to now, no biomarker has been found that clearly tells us which agent caused a specific cancer. But what can be done in the individual case? Of course, we need some answer with respect to this question. So one can try to calculate probabilities. And most of you will know that one can try to calculate a signed share, most frequently called probability of causation, although this term is not exactly describing what is done, but it's used quite frequently. And this assigned share can be estimated based upon individual characteristics, for example, the type of cancer, gender, age at exposure, age at diagnosis, the dose, and some factors in addition. Using this concept, you never can be sure that the specific individual cancer was indeed caused by radiation, meaning that you cannot attribute with certainty. You can give a certain probability, but you never can say this cancer was induced by ionizing radiation. And this is particularly true in the low dose range. So, coming to conclusions in this with respect to the attribution, and now I will say at least one sentence to deterministic effects, because there's a difference between the stochastic possibilities and the deterministic possibilities. An observed health effect in an individual, not in a population, but in an individual, could be unequivocally attributed to radiation exposure if the individual were to experience tissue reactions, often referred to as deterministic effects, and differential pathological diagnoses were achievable that eliminated possible other causes. And this is quite frequently possible. So with respect to deterministic effects, in the individual case, you can attribute this health effect. But other health effects in an individual that are known to be associated with radiation exposure, such as the so-called stochastic effects, cannot be unequivocally attributed to radiation exposure, because radiation exposure is not the only possible cause, and there are at present no generally available biomarkers that are specific to radiation exposure. An increased incidence of stochastic effects in a population you can attribute to radiation exposure through epidemiological analysis, but you have to keep in mind that the increased incidence of cases of the stochastic effects must be sufficient to overcome the inherent statistical uncertainties. And now, at least one sentence with respect to the hereditary effects. In animal studies, you can demonstrate hereditary effects, but in human populations, at least presently, you cannot attribute hereditary effects to ionizing radiation. This may be due to the large fluctuation in the spontaneous incidence of these effects, but there's a lot of discussion whether hereditary effects are inducible at all in humans. In general, increases in the incidence of health effects in populations cannot be attributed reliably to chronic exposure to radiation at levels that are typical of the global average background levels of radiation. So these doses are just too low, even in the case of populations. I told you, starting at about 100 millisievert upwards, you can attribute those effects to ionizing radiation, but not in the range of the usual background, so 2-3 millisievert per year. The reasons, the uncertainties associated with the assessment of risk at low doses, the current absence of radiation-specific biomarkers, and the insufficient statistical power of epidemiological studies. So the populations you have to study are just by far too big to manage them. And therefore, and this was a conclusion that Ansgar stressed very much, it is not reasonable to multiply very low doses by large numbers of individuals to estimate numbers of radiation-induced health effects within a population exposed to incremental doses at levels equivalent to or lower than natural background levels. But there might be an exception, because one has to keep in mind that public health bodies need to allocate resources appropriately, and this may involve making projections of numbers of health effects for comparative purposes. This method, though based upon reasonable but untestable assumptions, could be useful for such purposes, provided that it were applied consistently, the uncertainties in the assessments were taken fully into account, and it were not inferred that the projected health effects were other than notional. I will give you an example where this aspect might be important. Scientific knowledge can be applied to compare the potential benefits and risks of various types of imaging procedures used in medicine. You have always the problem, being a physician, to decide which is the best method for diagnosis in your patient, in particular when there are alternatives available, because radiation usually not the only possibility to make a diagnosis. There are other possibilities, and then you have to decide which is the best one for the patient, and then you have to take into account risks due to these diagnostics. And for example, there might be the question of the impact of CT diagnosis in a specific year in a particular country. And the current use of CT scanning in the United States may result in a future increase of about 1.8% above the current cancer rate. And you see the 95% confidence are also mentioned here. And this estimate now can be used to compare it with the potential impact on health effects by alternative diagnostic procedures. And so there is some value to do such a calculation, but you must stress that it's not clear that this increase will actually happen, or if it happens, that you can observe it. So the challenges for the next decades. And this is a little subjective, but I think that's one of the reasons why I'm here, to at least give you an impression what might be the challenge for the next decades. And first of all, we know a lot about radiation health effects and health risks in the high dose range, and also in the medium dose range. But we do not know very much in the low dose range. And one of the questions, is there a tumor risk below about 100 millisievert in the general public, or about 10 millisievert in the fetus? I will not talk much about the special case of the fetus. This would fill at least half an hour. But obviously, the fetus is somewhat more sensitive with respect to this question, but we are not really sure whether the 10 millisievert is a reliable number for some sort of a detection level. What does it mean for health effects that doses in the range of some millisievert can induce biological effects, such as damage to the DNA? We are well aware that 1, 2, 3 millisievert can induce biological effects. Simon just showed gamma H2AX4C, for example, that respond after 1, 2, 3 millisievert. But what does it mean for the health effect of an entire organism? Up to now, we don't know the consequence of these biological detectable effects. Do we know already all relevant biological mechanisms in the low and very low dose range, and what can we conclude from the known mechanisms? I will show you a picture in a few minutes, listing some of these mechanisms, and we are not sure whether these are all the mechanisms that we have to take into consideration. How does the dose-response curve look like for cataracts and circulatory diseases? Is there a risk in the low and very low dose range? This, of course, is a very, very important question with respect to radiation protection. And we have the reduction of the dose limit for the lens of the eye from 150 millisievert to 20 millisievert. You can discuss whether this is really appropriate, but we don't have the answers with respect to the effect in the low dose range, and in particular with respect to possible threshold doses, for example. So what I think is most important for the next decade, that radiation epidemiologists and biologists work together. I know that there have been attempts in the past, and I know that some publications appeared that described how this cooperation could work. But up to now, I have the strong feeling that the result that is expected has not shown up to now. I think it's one problem is that the language of the epidemiologist and the language of the radiation biologist is quite different, and it's very difficult to come together and understand one another. But there are a lot of merits if this would be successful in the future. So the study of biological mechanism, particularly in the low dose range, because for the epidemiologist, the advantage is this may help to decide which shape of the dose-response relation in the low dose range is correct, linear or linear quadratic, or maybe threshold, or maybe upward curvature. So maybe the study of the biological mechanisms help with respect to the answer. So this again is a picture that I showed some time ago. And our hope is that those biological mechanisms that are known, and maybe there will be some additional coming up in the future, that they will help to describe the shape of the dose-response curve. It will be difficult because in essence it would mean that we have to quantify the effect of all these mechanisms and put them together into one number. This might turn out to be very difficult, but I think it's worth the effort. So, identification of people who are prone to develop a cancer. the help for the epidemiologist might be to narrow the high variability of the spontaneous rate of malignancies, because those people who never will develop a cancer in some sense dilute the population, and in particular those individuals we are really interested in, those that really will develop a cancer, because about half of our population will never experience a cancer. The other half will experience a cancer. So, and identification of biomarker of radiation-induced malignancies. The advantage, avoidance of dilution of the number of cases due to other agents. But this sounds so simple, but there are some problems with respect to that. And I'm not convinced that we will ever find a biomarker in this sense. I'm still hoping that we will, but I will tell you why I'm so reluctant to think that we will find a biomarker. So can we really expect to find such a biomarker? Because I think we are all in agreement that there's strong evidence that carcinogenesis is a multi-step process. It's not just one step and then you have a cancer. Mostly 4, 5, 6 steps are necessary. Most likely, ionizing can induce all necessary steps. But in many, maybe in all cases, other agents may do part of the job. So it's not just ionizing radiation that is responsible for a specific tumor. There are other agents that help. And maybe step number 2 is done by a specific chemical. Step number 4 is done by ionizing radiation. And maybe in the other person, it's vice versa. So step number 2 is done by ionizing radiation. Thus, we cannot expect to find a pure radiation-specific biomarker, but at best a biomarker indicating some contribution by ionizing radiation. And the question is it realistic to find such a biomarker? I'm afraid that all are familiar with the idea that cancer is a multi-step process, but mostly it's just ignored that this is the background of all this. I still hope that there will be some sort of a marker that tells us at least a little bit about the attribution that comes from ionizing radiation, but I'm not sure that we ever will find it. The situation is just too complicated. So you can read much more about this problem, these problems, because Anskia, in its 2012 report that actually appeared about 2016, I think, so it's comparatively new, and there you find also answers to the high doses, so with respect to the mechanistic effects, and I can recommend to you to read this publication very carefully, and then I think I'm at the end of my talk.
Thank you so much. A few questions?
Okay, my name is Nils Kadersjö. Thank you for a very good, interesting presentation. I had one question. With the unit sievert, we have a problem with that unit since it's can relate to two quite different quantities, both the effective dose and equivalent dose. In what way did you use it during this presentation? Was it always effective dose?
So the 100 millisievert that was effective dose. Because this is something I should also have addressed, because the 100 millisievert is, of course, for all cancers. If you look at a specific cancer, and then you will have equivalent dose in that case. The limits are much higher. So the 100 millisievert effective dose is just for the entire group of cancers. And if you look at a specific cancer, let's say lung cancer or breast cancer or whatsoever, you need much higher doses than the 100 millisievert to get a statistically significant result.
Thank you.
One more.
My name is Ingmar Lund. Thank you for a very good presentation. I had a question about when you talked about the genetic effects and environmental issues and why we never can find the biomarkers. Also, I think one important thing could be random changes, which was never mentioned neither by you or by the former speaker, because there are indications that many mutants could be just by random mutations.
Are they really random, or they are also induced by something, but we just don't know, and then we call it random?
True, but there are studies then with populations and there are studies with environments, and well, maybe you're right. Maybe they might be induced by something, but there is nothing proved that there could not be random changes.
Yeah.
Because our blood cells are, for instance, renewed with a certain frequency and so on. So it's not unlikely that certain changes are just random.
Yeah, of course.
I'm not saying it changes anything in your arguments. It's only that they don't necessarily have to be either by other mutagenes. That's my point. In some sense, they are environmental, of course.
Yeah, but I still have the feeling that we just call them random because we don't know the cause that makes the randomization.
That might be true, yes.
Yeah.
Yeah. But
Thank you.
it was a comment, though.
Yeah.
Great presentation. Thank you. Our final talk before the break, current issues on secondary primary cancers after radiotherapy. LeBaron Jacobs from CE France. Everything's working now.
Yeah. Thank you, Chair. So first of all, I would like to thank all the organizers, and especially Ingmar Lund for inviting me in this conference. So now I'm going to have a talk about the current issues about second primary cancer after radiotherapy. That is a very controversial subject, but I'm going to give you a transversal view of this public health problem. First, what is the definition of second primary cancer? They are iatrogenic tumors that arise as de novo neoplasms in a field of therapeutic radiation after a latency period that can span decades and are not recurrences of the original cancer. We know that advances in radiation therapy and also chemotherapy have increased the survival rate of many patients treated for cancer today. However, radiotherapy is a double-edged sword. It has a well-established role in the curative treatment of various solid tumors, but it has also the potential to induce cancer decades after the treatment. And this is concerning as there is an increase in the number of long-term cancer survivors. So as I said, I'm going to give you a transversal view. So first, in epidemiology, we know that there is an uncertainty in estimating the exact incidence of second primary cancer because of the confounding factors such as patient style, lifestyle, and genetic susceptibility. And as you can see on this graph, although there are causes such as common etiology with the primary cancer and genetic or lifestyle predisposition, many of these second primary malignancies are treatment-related, especially in pediatric and young adults in survivors with a huge contribution of radiotherapy. Here is an article, so a publication from Barbaro about the incidence of second tumors of survivors of childhood Hodgkin's lymphoma treated with radiation therapy or not treated with radiation therapy. And they concluded that children with Hodgkin lymphoma without radiotherapy have a substantially lower incidence of second tumors than those treated with radiotherapy. So we are sure that age is one of the key parameters because children have 3 to 6 times more sensitive with regard to radio-induced carcinogenic effects compared to adults. And also for some types of cancers and some pediatric cancers, SPCs cause more death than the primary cancer. As children and young adults are likely to survive for a longer duration after anti-cancer therapy, so we know that they are at the greater risk of developing radiation-induced second malignancy. So the childhood cancer survival studies, so the authors have concluded that the risk of developing a second cancer in the first 25 years after treatment can be as large as 12%. And the mortality has increased and is due to second malignancies as compared to that due to other causes at 25 years after first cancer diagnosis. So now in the field of dosimetry, we know that dosimetry can help epidemiological studies because risk can be placed in perspective, and future retrospective epidemiological studies may rely on accurate organ dosimetry. And so we know that in dosimetry, with dosimetry studies, most frequently radiation-induced neoplasms occur in volume exposed to high doses. However, the impact of low doses in radiation-induced carcinogenesis should be clinically considered because modern radiotherapy significantly increases the volume of tissues receiving low doses. So the use of modern therapy techniques such as IMRT, RGRT, stereotactic, and so on, is of many controversial issues in the pediatric age group in spite of their proven dosimetric distribution advantages. So according to the latest recommendations of the International Commission on Radiation Units and Measurements related to the remaining volume at risk, it is now accepted that the search for means is more accurately determining such doses is of renewed clinical interest. Moreover, a work from the Working Group 9 of URADOS concluded that there is a need of a robust foundation and methodology to measure or calculate organ doses following radiotherapy. And then a task group 158 from the AAPM, American Association of Physicists in Medicine, published in 2017 a report, and they concluded that there is also a need of measurement or some other means of assessing the dose due to the dramatic inaccuracy of treatment planning system outside the treatment field. So in dosimetry, it's of particular interest. Are the second cancer risk estimates for new radiation treatment modalities such as IMRT, IM80, and proton and heavy ion radiotherapy. The long-term risks from such modern radiotherapy treatment techniques are unlikely to become manifest for many years due to the long latency time for solid tumor induction and have therefore not been fully quantified. Here you can see on this picture a dosimetric comparison of MRT, volumetric modulated arc therapy, and also stereotaxic body radiation therapy and low-dose radiation therapy. And you can see here the different isodose lines corresponding to 100% for the red line of prescription dose, and then for the blue one on 25% of the prescription dose, and in yellow, so just here, it corresponds to 50% of the prescription dose. So now, the quantification of the correlation between dose and risk is affected by the uncertainties. It's a huge problem. And this uncertainty are involved in relating a tumor which was induced decades after the treatment of the primary disease to the actual dose at the tumor site. So now we know that the dose outside of the treatment volume cannot be predicted by clinically used treatment planning systems. And then the remaining uncertainty is about 40%. So there are also other dosimetric uncertainty, including patient movement, impact of fractionation on the dose distribution, anatomical changes, and simplified dose reconstructions. Okay, thank you. So in the case of prostate cancer, it has been proved that secondary long-term effects are of interest because it's due to the large number of prostate cancer patients treated with radiation and due to also 50% reduction in mortality after treatment. So it's a good news. However, there are unwanted secondary radiation, such as neutrons and leakage photons, when people are irradiated by clinical linear accelerators. And this unwanted secondary radiation can be generated and after that be absorbed by healthy tissues located outside the target radiation field. So we need direct dose measurements of peripheral distant organs to evaluate both photon and neutron dose contribution because the systems used, so the models used, don't, for the moment, don't taken into account the neutron dose contribution. Out-of-field dose measurements can aid in the assessment of secondary primary cancer risk, so an aspect that is gaining more importance in today's radiotherapy treatment planning and delivery. This is a publication, a recent publication, 2017, about the risk of second primary cancer due to peripheral photon and neutron doses. And the aim of this article is to determine the risk of second primary cancer in the organs distal to the prostate target volume during a 3D conformal radiotherapy. So the contributions of secondary neutron doses produced by high-energy photons were taken into consideration for SPC risk estimation. Another thing, so peripheral photon and neutron dose equivalents were measured using TLDs in a Rondo phantom. And then quantification of the risk in developing SPC in various normal tissues or organs were done by the application of the competitive risk model, including parameters of induction of DNA mutations at low doses and also cell killing at higher doses. And the authors concluded by their results that there is an increased risk of SPC development of normal organs distal from the target volume. So they have shown that the estimated risk of SPC in rectum and bladder were relatively small compared to those of thyroid and esophagus. The importance of actual radiation dose measurement for clinical treatment planning evaluations in terms of estimation of SPC risk is highlighted by the secondary neutron dose contribution and also the higher radiobiological effect of neutrons relative to photons. So there are radiation protection implications from this article. So this implication is to provide radiation protective measures for the patient during high energy external beam irradiation of the prostate using, for example, multi-leaf shielding, or alternatively, it could be used, so lower beam energy in order to minimize production of photoneutrons. And then, depending on the disease staging, we could apply a high-dose rate brachytherapy treatment. So now, in the field of radiobiology, we have also some issues because exposure to low-dose radiation is known to cause base damage, such as single-strand DNA breaks and double-strand breaks. These double-strand breaks could lead to gene mutations. But, which is important also, it's the impairment of the DNA repair proteins, which normally protects against DNA damage, could lead to increased susceptibility to radiation-induced SPC. For example, as mentioned by Simon, the mutation affecting atalaxia mutated, ATM, it's a protein which senses DNA damage and initiates a repair cascade. These mutations can lead to increased radiosensitivity and also cancer susceptibility. Moreover, it has been observed that radiation dose less than 200 milligray fails to activate the G2M cell cycle checkpoint. This could result also in failure to repair DNA damage and could result in carcinogenesis. So there are also another mechanisms that have been proposed to account for SPC at site distance from the primary treatment area. It is the radiation-induced bystander effect and also tissue inflammation. Bystander effect involves intercellular communication through gap junctions and systemic cytokine signaling. But for the moment, there is no consensus on a precise designation of radiation-induced bystander effects, which involve a number of distinct signal-mediated effects within or outside the irradiated volume. So several cellular mechanisms were proposed, such as secretion of soluble factors by irradiated cells in the extracellular matrix, or the direct communication between irradiated and neighboring non-irradiated cells via gap junction. This phenomenon is observed in the context of major local inflammation linked with the global imbalance of oxidative metabolism, which is very challenging for in vitro experiments. So now we are sure that the other major challenge in assessing radiation-induced secondary cancer risk is the limited understanding of the complex biological processes involved in radiation carcinogenesis. So we hope that advances in molecular biology, genomics, bioinformatics, and mathematical models can allow to understand the underlying mechanism that may predispose or determine malignant transformation after radiotherapy, and to predict radiotherapy-induced cancer risk. Here is a publication, so a recent publication. The authors studied the genomes of 12 radiation-associated SPC of 4 different tumor types: osteosarcoma, spindle cell sarcoma, angiosarcoma, and breast cancer. So they identified 2 signatures in the end, an excess of balance inversion, and change that these balance inversions, are changes in gene order, but there are no loss or gain of DNA. And also another signature, small deletions in radiation-associated SPC. So we have a lot of issues on this primary cancer in terms of radiobiology. What are the molecular mechanisms of radiation-induced cancer, especially in this field? The issue of genetic susceptibility is the possible presence of different mechanisms at low and high doses, and the problems of doses per sessions and radiation quality are all the questions also, and the role of microenvironment in modulating inflammatory reactions in tumor generis. And are there bystander or systemic effects? Can a genetic mutation or polymorphism that is associated with the primary cancer affect the risk and the mechanism of radiation-induced carcinogenesis? There is a special mention about issues on radionuclide therapy. So there are some studies which conclude that the initial results indicates that the risk of radiation-induced cancer from radionuclide therapy are on par with those predicted for external beam radiation therapy. And also some studies concluded that the risk of radiation-induced leukemia is potentially greatest given the differences in dose distributions involved. So it is imperative that more attention be afforded to investigating the cancer risk associated with radionuclide therapy. So my conclusions are perspective or issues about SPC. So first, what are the risks of developing SPC after radiotherapy for different treated sites, and how are they affected by the ever-changing technologies used? How can we optimize their risk without sacrificing the therapeutic benefits of radiotherapy? It's very important. We have to improve radiation therapy techniques and the follow-up of patients after radiotherapy. It is done, but it has done for longer time, and especially for young people. We need to promote a rigorous dosimetric framework to test future models and to assess retrospective doses to contribute usefully to epidemiological studies. Then, cancer treatment has largest impact on SPC risk among patients treated for a first cancer at a young age with excellent prognosis. So sex and age at time of childhood cancer diagnosis are important host-related factors, because some study also showed that females are more sensitive regarding the SPC risk. The impact of etiological factors of the first cancer and of cancer treatment characteristic for the first cancer and risk of second cancer has to be considered. And then a very important issue is the molecular epidemiology that could improve our understanding of the pathogenesis of SPC by identifying specific pathways, such molecules and genes that influence the risk of developing SPC. So now we know that we have to address future research needs to explore how genetics and radiotherapy interact. It's very important, as well as the link between radiotherapy and other cancer-causing agents, and to promote the development of new cancer screening strategies, sensitive and precise biomarkers of risk, and also early detection of second primary cancer. It's very important for young people. So it is not my intention to recommend a therapeutic procedure for radiation oncologists and so on. But the goal is to point out the carcinogenic risk, if any, of the newly introduced radiotherapy techniques in order to help radiation oncologists to select the best technical approach and to optimize the parameters of their protocols or clinical trials for specific patient population to deliver the optimal dose to the tumor while minimizing the risk of second primary cancer. And now I think it's a very important thing. It's currently the time of personalized care. So I would like to thank you for your attention, but I would like also to thank a lot my French colleague from CEA and RSN, and also my colleagues from Sweden, from Argentina, and from Peru for helping me to build this presentation. Thank you very much.
I think we have time for at least one question. Rock?
I'm going to be talking a little bit after the break about these topics, but the 40% uncertainty in the dose outside the field is probably at the high end. Better treatment planning systems are able, at least in the planes that the cancer is affected, because you have CT information there to calculate the dose. They're actually a lot more accurate than that. It's outside the field, a long way outside the field where the 40% estimate is, and that's important. And the only way you can get that is to do a whole body CT, which of course adds to the unwanted dose. However, in terms of that estimate, I think it would be very worthwhile to actually, especially in younger patients, to do the whole body CT so that you can calculate the dose. And if you use Monte Carlo, it's pretty accurate. The other thing is that pediatric cancers are increasingly being treated with protons, which I think is appropriate because you have a factor of 2 or more reduction in the integral dose. And then finally, a lot of machines were never designed for IMRT. So you can add shielding such that the unwanted leakage radiation is much, much lower. And the integral dose that's actually given is not changed. But what you are right is you're giving a low dose bath to a larger volume. This reduces the deterministic effects to the patients, but it may
It's
increase
right.
the stochastic risk. So I think that's the important comments. And we can talk about it at the panel
Thank you.
as well.
You're right. Thank you very much.
Thank you. Did I see one over here? Oops, you got.
My name is Pavel Olko. Thank you, Lawrence, for the very nice presentation. You mentioned the need for the dosimetric research and the lack of the data. In the last 10 years, there was a lot of publication, and you see done also by the Working Group 9, where you mentioned Urados. And there's a whole bunch of experimental data of phantom measurements, anthropomorphic phantom measurements for classical and for the proton oscillotherapy. And now this is benchmarked also to Monte Carlo, and as Thomas said, that this is very good correlates. So in principle, this is ready really to be implemented to all treatment planning system, and then that will be quite easy to get the estimates for epidemiological studies.
Yes. I think that the link between dosimetry and epidemiological studies are very, very important. Yeah.
We have a clustering effect.
A specific question about I think it was Bezak et al., the Physica Medica. You talked about that there was a lot of neutron dose for the proton treatments. What energy were they using for those treatments?
It was 10 MeV energy.
Okay. Because
Yeah.
I mean, I'm not sure whether the simplest solution would be to go down to 6 MeV, which is where most people do their prostate treatments anyway, and just get rid of the neutrons altogether, I would expect.
Yeah.
I mean, even 10 is
10 MeV, yes.
more than you need.
So,
We do have one over here.
yeah.
Thank you very much for your very nice presentation and very comprehensive lecture. As a radiation oncologist, I will certainly not deny at all what you have said, but just I think we need to be adequately balanced in what you say, in what you said. Sorry, all the data that you have shown, by the way, I haven't seen a lot of numbers, were typically gathered 15, 20 years ago, where indeed, as was mentioned by the first comment, the way the dose was calculated, the way the dose was produced, with the neutrons produced in the head of the collimators, which is not the case any longer with the use of flatten-free filters machine. Obviously, we clearly need to keep a strong eye on it, but we still have to admit that all the progresses in the equipment, in the way the dose is calculated, in the way the dose is delivered, in the IMRT treatment, in the use of protons, obviously goes in the same direction, which is to further decrease what was potentially indeed a risk for patients. Indeed, when you compare population of patients that got treatment with surgery and or with radiation, you see indeed a little increase in the risk, but you also have an increase in the risk of second cancer induced by whatever, for sure not by the knife of the surgeons, as far as I can know, in the surgical treated population. So we need to be extremely careful in associating, as you mentioned, so I don't deny what you have said, you did it properly. We have to be careful in associating a cause to what is observed indeed as increased risk of cancer in population which already got one cancer.
Yeah. Thank you very much.
Last one.
Well, Christian Streffer, I certainly also thank you very much for this interesting talk and especially the perspectives. Well, I think if you talk about the studies where you see today the secondary cancers, this was Hodgkin lymphoma, and it was treated, the patients were treated 30, 40 years ago. And then, of course, you had quite often half-body treatment. Vast regions of the treatment, and this you have to consider, of course. I completely agree with you. Modern planning systems are so good that this will be very restricted. But I think you have to discuss this, or if you have to consider this, if you discuss the data about which you are talking.
Yes, of course.
Thank you very much.
Thank you. Thank you.
Thank you. Coffee break? And what time should we be back?
Yes.
3:20? 15:40. 15:40 it is. Thank you.